Greetings and welcome to Lesson 2.5 Formulas. In this lecture, we'll concentrate on equations with more than one variable. Primarily, we'll focus on equations with two variables, but occasionally three. We've actually worked with formulas up to this point. We just didn't call them formulas. And just as a refresh, a formula is an equation that contains more than one variable. For example, we've used the perimeter formula. P equals 2L plus 2W. We actually have three variables in this equation. Our P, the L for length, and W. So P for perimeter, L for length, and W for width. And as long as we have some information about two of these variables, we can solve for a numeric value of the third. If we're not given enough information, then maybe we can't solve for a numeric value. Possibly we'll be able to solve for some type of simplified version, maybe down to one variable, but we have to have enough information to get it down to a numeric amount. So here's an example. The perimeter P of a rectangular livestock pen is 40 feet. If the width is 6 feet, find the length. So we know the perimeter and we know the width. So the only unknown that we don't have is the length, so we're going to solve for the length. So if we do that, when P is 40 and W is 6, we're going to plug in the formula. P equals 2L plus 2W becomes 40 plus 2L plus 2 times 6. That's 40 equals 2L plus 12. We're going to subtract 12 from both sides, leaving us with 48 equals 2L. Our next step is to divide by 2. So our length is going to be 14 feet. So if a rectangular livestock pen has a perimeter of 40 feet, width of 6 feet, then the length is 14 feet. Let's try another example. Find y when x equals 4 in the formula 3x plus 2y equals 6. When x equals 4, then our formula of 3x plus 2y equals 6 will become 3 times 4 plus 2y equals 6. But 3 times 4 is 12 plus 2y equals 6. Now I need to move the 12, get rid of the 12 because I'm trying to isolate my variable y. So I'm going to subtract 12 from both sides, leaving me with 2y equals negative 6. Next, I need to, again, isolate my variable by dividing by 2. So my solution is y equals negative 3. And we should look back and see if that makes sense. So when x is 4 and y is negative 3, 3x equals 3 times x equals 3 times 4, which is 12. 2 times negative 3 equals negative 6, and 12 minus 6 indeed equals 6. Now sometimes they may not actually want you to solve for a numeric value. Sometimes they want you to isolate a particular variable. So they'll say solve for a particular variable. So given a formula like the equation for the area of a triangle, A equals 1/2 B times H, we want to solve for H. So we need to consider everything that's happening to H. And the first thing, we see that it's getting multiplied by 1/2 and also multiplied by B. Now, personally, I would suggest that you work with these one at a time. First thing I'm going to do is I'm going to get rid of that 1/2. Well, if I multiply both sides by the reciprocal of 1/2, then I would have isolated that portion that I want to. So I undo what's happening. Right now I'm multiplying by 1/2. So the undoing would be dividing by 1/2 or multiplying by its reciprocal, which is 2. So if I multiply both sides by 2, the 2's will cancel out, and I'm left with BH on the right-hand side and 2A on the left-hand side. But what else is now happening to H? Well, we're being multiplied by B, so if I divide by B, what I do to one side I have to do to the other side. So if I divide by B, then the B gets eliminated from the right-hand side and moves over to the left-hand side. So if I wanted to solve this for H, I would get it down to 2A over B equals H. So here's our rule. To solve a formula for one of its variables, we must isolate that variable on either side of the equal sign. All the other variables, all the other constants will go to the other side. And you might think, why is this helpful? Why is this useful? Because sometimes I might be solving for a particular variable and it might be easier to manipulate the formula first and then plug in everything that I'm given. And then you're just left with, for example, if I was given the area and I was given the base of my triangle, if I solve this for H first, then I just plug in my area and plug in my base, and then I'll have exactly what I'm looking for with the height. Let's try an example. We're going to solve for y when it's y minus 1 all over x equals 3/2. Now, the first thing we really need to think about is what is happening to y, and we need to undo it in a certain way that it makes sense. So when we're thinking about it, we can look at the whole entire side which y is sitting at, which is the left-hand side. And we know that a minus 1 is happening to it. So we have this minus 1, and we also have this division by x. Now we have to be very careful about how we undo this. So my first step is do what's happening to the whole entire side first. Well, right now that whole entire side is being divided by x. And if I undo a division, that's going to be multiplication. So the first thing I'm going to want to do, y minus 1 all over x equals 3/2. If I multiply this side by, if I multiply each side, oops, you see my pink color here. There we go. If I multiply each side by x, then the x's will cancel out on the left-hand side and will be placed on the right-hand side. Perfect. Now I'm left with y minus 1 equals 3/2 x. But I still haven't isolated y yet. There's one more step I need to do. Right now I'm subtracting 1 from the y. But I really need to add 1 to both sides. And then I will have y all by itself. And since 3/2 x and 1 are not like terms, I cannot combine them. But I can leave them as is, and that's fine enough. So we started off with y minus 1 all over x equals 3/2, and by solving for y, we now see that y equals 3/2 x plus 1. Now you might recall that we had complementary angles add to 90 degrees. So if x and y are complementary angles, then we know that x plus y equals 90. Well, we can solve for the angle y by isolating angle y. And if I do that, there we go. If I do that, all I need to do is get y all by itself. So I'm going to subtract x from both sides, so I know that the angle y equals 90 minus x. Likewise, I can turn it around and I could say let's solve for x by subtracting y from both sides, and therefore x equals 90 minus y. And we can say the same thing for supplementary angles. Two angles that add to 180, well, we can solve for, let's go here, we can solve for our supplementary angles by saying the same thing, x plus y equals 180. But that also means that x equals 180 minus y, and y equals 180 minus x. Now this comes in handy when you're asked, find the complement and supplement of an angle of 25. I'm given one of the angles, so I'm given something like y equals 25. I can solve for x. So if it's a complement angle, x will equal 90 minus y. We know what y is, so it's 90 minus 25. Therefore, our complementary angle is 65. Likewise, I can use that x equals 180 minus y, use what I know for my angle y, plug that in, and therefore my supplementary angle to 25 is going to be 155 degrees. So let's change gears just a little bit and talk about basic percent problems. There's some very common, I would say, common percents, common fraction to decimal to percent that you really should kind of have in your memory. So let me run through these really quick. They make your life a little bit easier when you can remember them. I'm not a big one on memorization, but a couple things you should just be able to know really quickly. For example, fraction of 1/2 is equivalent to 0.50, which is the same thing as 50%. Percents are just a comparison to 100. Okay, so keep that in mind, comparison of 100. Next common fraction would be 1/4. In decimal format, that's 0.25, and that's also 25%. Another common fraction is 3/4, which is 0.75, 75%. 1/3 is 0.33, well, with the bar, because 3's never end. And you have two ways of looking at it with percent. One is the 33 and 0.3 with the bar percent, or 33 and 1/3%. Either one of these work for the 1/3 in terms of percent. 2/3 is very similar. It's going to be 0.6 with the bar, or 0.66 with the bar, or 0.666 with the bar. In other words, in percent, it's going to be 66.6%, or 66 and 2/3%. 1/5 is very common. That's 0.2, which is 20%. 2/5 is 0.4, 40%. You can imagine what 3/5 is. Well, that's 0.6, 60%. 4/5 is 0.8, and that's 80%. So those you usually want to have in your arsenal of just that you know. So you want to be able to be given a fraction and convert it to decimal. All you need to do is divide the denominator into the numerator. For example, this would be 5 divided into 2.00. So we want at least a couple of zeros. 5 does not go into 2, but 5 does go into 20 4 times, so it's 0.4. So you do want to be able to do that conversion. It's the denominator into the numerator. If you're given the decimal to convert to percent, you just multiply it by 100. So in essence, you move the decimal over 2 places to get to the percent, and you need to add that percent sign. That percent sign means something. It's symbols in math. So you need to remember not to drop the percent symbol. 40% does not equal 40. Those are completely different things. So let's try a couple of examples. There's always a good way of setting up your problem, and here's how I remember it. It's my percent amount is always compared to 100. And then what number we call the amount is over the whole number of what number? Well, that is our base. And you'll see this come together in just a second. So what number? We don't know. We're actually looking for our number. We don't know our amount. We are given our percent and we are given our base. So if we fill in this table, we then only need to isolate the amount. And I've kind of done that really quickly. So if you can imagine, let's see, 25%, our amount, we don't know, that is our x. Our base is 60. 100 divided into 25 is going to give us our 0.25. That's right here. 60 is under our x, so to undo a division, we multiply both sides by 60. Therefore, it moves over to the other side. And 0.25 times 60 is 15. Now let's try this again, setting up what percent of 24 is 6. Now given, we don't know what percent, so that's going to be our x. We do know of 24 is our all amount, that is our base, and 6 is our part. Okay? What percent of 24 is 6? Now what I need to do is I need to undo what's happening. So right now to the x, I need to multiply both sides by 100. That gets rid of my 100. Okay, so now I am left with x equals 600, oops, sorry about that, over 24, and I can reduce that. So 6 goes into 24 4 times, and 6 goes into 100 100 times. I'm just reducing it, but 4 goes into 100 25 times. Therefore, what percent? The only thing I need to remember is I need the percent marker. What percent? 25%. Okay, this third type of question that it can ask me is 45 is 75% of what number? Now, it's my base I'm looking for. So I'm going to set it up of 75 is to 100. I know my 45 is to I don't know what, but I need to isolate that variable. So the first thing I'm going to do is multiply both sides by x. Okay? Or, here's a trick, flip them both. Okay? If you flip both sides, the x becomes on top, and that's totally allowable. So if I flip it, it's going to be 100 to 75 equals x to 45. Okay. Now my x is on top. I flip both sides, so that's legal. I need to isolate my x. So the way I'm going to do that is I'm going to first multiply by 45 to both sides. Okay. 45s go away. I'm going to do some reducing right now, just because I see it. I do know that 15 goes into 45, let's see, 15, 30, 45 3 times, and 15 goes into 75, 15, 30, 45, 60, 75, 5 times. Okay. I also know I'm just trying to reduce as best as I can. 5 goes into 120 times. So 5 goes into 120 times. So the only thing I am left with is 3 times 20 is 60. X equals 60. Okay. So I know that's a little messy, but I was just reducing. So how could we use something like a formula? Well, we do use all kinds of formulas. One is conversions. We have a lot of conversions. The U.S. likes to use different measurements than just about the rest of the world. So we do have some conversions. For example, in temperature, the U.S. uses Fahrenheit, and lots of other places use Celsius. And there's a nice formula that we can convert one type of temperature to the other. So given a formula, or given the value in Fahrenheit, I can plug it in to this formula right here. 5/9 times the quantity F minus 32. My Fahrenheit value minus 32 will give me what it is in Celsius. Likewise, if I have Celsius and I want to know what it is in Fahrenheit, we do use formulas quite often. One of the formulas that we use is a conversion from one temperature to the other. In the U.S., we use Fahrenheit, and in just about the rest of the world, they use Celsius. And they're not a one-to-one temperature. Otherwise, we wouldn't need two of them. But there is a nice formula that we use to be able to convert back and forth. If given a temperature in Fahrenheit, I can convert it to Celsius by first subtracting 32 and then multiplying it by 5/9. That will give me Celsius. If I'm given Celsius, if I multiply it by 9/5 and then add 32, that will give me Fahrenheit. For example, I know water freezes at 32 degrees Fahrenheit. Well, 32 minus 32, well, that's 0, and 0 times anything is 0, so that's equivalent to 0 Celsius. And room temperature, let's say, is 68. If I was to plug 68 in there, I would have 68 minus 32 is going to be 36. 9 goes into 36 4 times. 5 times 4 is 20 degrees Celsius. So you see how given one type of temperature, you can convert to the other type of temperature. There is a way that we can approximate this. The true formula is a little cumbersome, and there is a way to estimate it. So let's say our friend Bob travels to Buenos Aires and a group of friends with him, and it's a hot day. One of the bank's kiosks indicates the temp is 25 degrees Celsius. One of the friends estimated the temp in Fahrenheit degrees by multiplying by 2 and adding 30. So what's the approximated temp? So we're going to take 25, multiply by 2, which is 50, add 30, which is 80. So 25 degrees Celsius is approximately 80 degrees in Fahrenheit. Okay. The actual temp is going to be that conversion. So let me scroll up a little bit so you can see the conversion. So I have 25 degrees Celsius, 25. Well, 5 goes into 25 5 times. 9 times 5 is 45, plus 32 is going to be 77 degrees Fahrenheit. That's pretty darn close to our estimate, 77 degrees Fahrenheit. So why does the approximation formula work so well? Okay. Well, if we take a look at the formula, let me erase some of my drawings here all over it. When we look at this, 9/5, when you think of that, that's really super close to 10/5, which is 2. So this 9/5 is approximately 2, and 32 is really close to 30. So by multiplying the 2, I go a little bit over, but then by just adding 30, I'm a little bit under, so it's a pretty good approximation. And if we wanted to estimate, last question here, if we want to estimate Celsius to Fahrenheit, then what we do is we take the Fahrenheit minus 30 and divide by 2. That would be the opposite of multiplying 2 and adding 30. First we have to subtract 30, then add 2. Alrighty, so let's go back and start solving for variables again. And I know it can get a little bit difficult as to where do you start, but you do first want to find the variable that you're solving for, and in this case we're solving for y. And you got to figure out what the heck is happening to not only y, but that whole entire side. And what's happening to the whole entire side gets undone first. Right now, I'm adding 3x to the whole entire side. So the first thing I want to do is subtract 3x. Subtract 3x. Now I have 2y equals negative 3x plus 6. Now it doesn't matter if you said 6 minus 3x or negative 3x plus 6. Same thing. Doesn't matter. The next thing I need to do is what's happening to y. Right now I'm multiplying by 2, so I just need to divide by 2. Divide by 2, the whole entire side, not just one little old thing. Now I'm left with y equals negative 3x plus 6 all over 2. Now you could leave the problem this just as it is, or you could break it up, 3 halves x plus 6 over 2, but 6 over 2 is 3. So y equals negative 3 halves x plus 3. Either one would work. Alright, so let's solve for v in this looks like very complicated equation. H equals v times t plus 16t squared. And I want to solve for v. So again, we need to think about what's happening to the whole entire side, what's happening to v. Right now, this whole entire side, we are adding 16t squared. So I have to undo that addition by subtraction. So 16t squared, subtract 16t squared. H and t's cannot be combined. So the left-hand side becomes h minus 16t squared equals v times t. Now the only thing left that's happening to v is multiplication by t. So to undo that multiplication, I divide each side. So my final is h minus 16 t squared all over t equals velocity. So why is that good to know? And the reason is I might be given my height, that's h, I might be given time, that's t, and I'm looking for velocity, and now I can solve directly velocity. Instead of finagling velocity with a time, I've already solved for velocity. Now in physics, your first term of physics, you'll learn this formula, and it's very similar to the one that we manipulated, except the only difference is there is a minus sign in there. So h equals v times t minus 16t squared plus s. Now, h is for height in feet at any given time. S is the initial height in feet. T is time in motion in seconds. And v is your initial velocity in feet per second. So when s is 0, we get a formula very similar to the one that we had above. H equals vt minus 16t squared. So we're not going to get into physics in this class, but there is a relationship to what we're doing in ours and actual science out there. So I think that's it for this video that I want to cover. Until next time, be seeing you.